Hi, welcome back to the Elementary Psychometrics Laboratory, as I'm calling it, otherwise known as my home office. And we're going to have a pretty short little meeting today on the subject of the standard error of the estimate. So this is a validity-related topic having to do with the accuracy, or rather inaccuracy, of our predictions. Without further ado, let's jump into sharing mode here. See how we do. There we are. So again, mostly a how-to today with a little bit of conceptual stuff mixed in. So what are we talking about? Well, we're trying to use test results to make predictions, to generate predictions, whether in the future or perhaps simply estimates as to what might be happening right now. And like everything else, these estimated outcomes are subject to random error. Getting used to random error by now, aren't you? So, I may have some test results that predict that yes, you will earn a 3.58 GPA in your college career, but I don't know that. It's an estimate. What I have is a more or less approximate prediction that's based on some kind of an assessment, which, of course, is not perfectly valid. Measures are not even perfectly reliable. That is, they don't measure anything to perfection, and the relationship between what the test is doing and what we're trying to understand in the real world, or the theoretical world for that matter, is also imperfect. So there's two sources of imperfection here. So what? The standard error of the estimate basically captures that uncertainty, given are the known properties of the test, the assessment, and the outcome, whatever that might be. So conceptually, it is a lot like the standard error of measurement, something we've studied before, but with not only one, but two sources of random error, not only the limited reliability of the measure, which is what the standard error of measurement captures, but also its even more constrained validity at predicting, again, the real world or ideal world, for that matter, outcomes. So, yep, there's an equation for that. We'll walk through it. It's not a super fancy equation. I hope nothing here looks terrifying at this stage in your training. So, what do we need? Well, we need to know the correlation between the predictor, typically our test score, and whatever the outcome, the criterion happens to be. That's basically a validity coefficient, right? And so we need that. We need to have some idea of how valid the test is for the stated purpose that we're using it for. And we need to know the standard deviation of the outcome of whatever it is we're trying to predict, not the standard deviation of the test. Classic error to make on, say, a homework assignment there, right? Uh, and again, this is the equation then. The standard error of the estimate is equal to the standard deviation of the outcome or criterion, that's supposed to be a little subscript y there, times the square root of the quantity, 1 minus the correlation between test and predictor squared. Uh, that's it. The only thing that looks different there than in the standard error of measurement equation is that here the correlation is actually squared. Yeah. So, how do we get it? Some of you are probably already running sample problems for yourselves, in your heads because you're better than I am. But let's, slow it down for the rest of us. Again, I have to have those two things. So first, I'm going to square that correlation. Then I'm going to subtract that from 1. Wow. By the way, since correlation coefficients are always less than 1, the squared correlation coefficient will also always be less than 1. Correlations, of course, can be negative. That doesn't stop them from being strong predictors. The squared correlation, however, will be a positive number. So squared the correlation, subtracted it from 1. Now take the square root. That's, got your little calculator out. You're probably keeping up with me already if you made up some numbers. And then just multiply that times the standard deviation of whatever it is you're trying to predict. And again, it is important to remember to square the correlation. For one thing, if you don't, you'll be wrong. For another thing, if you don't, and it happens to be a negative correlation, you're going to be way wrong. So, okay. And again, the other error I see people make when they're trying to do this, by hand over the calculator, is to use the wrong standard deviation. Easy way to remember that is to just think of two variables that have really different variabilities around them. For example, if you took something like SAT scores, where the standard deviation is roughly 100 points, and you took grade point average, where the standard deviation is going to be under 1 point, right? Because it's only a 5 point scale, 0 to 4. It wouldn't make sense if you used if you're using the SAT to predict grades, which is kind of what it's for, and you said, oh, well, I'm predicting that you're going to have a 3.58 GPA plus or minus 80. I mean, that doesn't make any sense at all, but that's the kind of result you could get if you used the wrong standard deviation. All right. So anyway, here's an example calculating it. So we have, we're prison psychologists now. Whether you want to be or not, that's your job for the next minute or two. And so you're being asked to consult as to how suitable inmates are for early release. So you do a study of 200 who are going to be released. They all are evaluated using the Hare psychopathy checklist, standard measure for psychopathy, and you follow them for 2 years. And at the end of 2 years, you tabulate how many times they've either been arrested or cited for parole violations. And you find that there is a correlation of 0.45 between how psychopathic they are on the one hand and how many violations they have on the other hand. Now, a lot of folks end up with at least a few parole violations, so these adverse events add up to an average, I'm making this up, of course, of 15 with a standard deviation of 4. In other words, most of your recently released folks in this make-believe example have somewhere between about 11 and 19 violations, but some have fewer, some have more. So if I want to use PCLR scores to predict recidivism risk in the sense of how many violations there are going to be, and I generate a prediction for you, then, well, no, you're the psychologist, but for whoever's in the room listening in as you listen to this, what's the standard error of the estimate? So again, square the correlation, we get 0.2025. Subtract that from 1, we get 0.7975. You can round off a little more than this if you want to, but I always say stay about at least 3 to the right of the decimal until you're done, then round to 2. Anyhow, square root of that comes to 0.893, and we multiply it times 4, the standard deviation of the the adverse events count, and we get something like 3.57 or 3.6. Ta-da! You have it. We don't need to do a practice. If you want, you can do a practice on your own. So I'll give you an example here. You've got a creativity test, a little more fun than prison work, baby. And you want to predict how many paintings art students will submit to juried exhibitions during a 3-year MFA program. I don't know why. Maybe you're running the admissions or helping to run the admissions committee for the school. So the creativity test has a mean of 100, standard deviation of 20. That might be the Torrance tests of creative thinking, for example. And you looking at past data, you know that on average, the students submit about 12 paintings with a standard deviation of 8. So most are somewhere between about 4 and 20, though some are submitting nothing and some are submitting quite a bit more, quite a few more. The correlation between creativity test score and the number of paintings submitted comes to 0.64, a nice robust correlation. I don't think it would really be that high, but it's make believe. So what is the standard error of the estimate? So we'll kind of let you set that one up for yourself if you want. I'll kind of go slowly here. But of course, the critical numbers here are 0.64, the correlation, and 8, the standard deviation of the number of paintings submitted, because that's what we're trying to predict. So you could set it up however you like. And something you might have noticed, by the way, is even in that first example, you can always pause me while you crunch the numbers if you wish, but now you're back because you could pause me and resume. Something you probably noticed is that there was still a lot of uncertainty in our prediction. Yeah, the behavior of individuals is not easy to predict, no matter what test you have. So even though you have a test that's has a pretty high degree of validity, I mean, a correlation of 0.4, 0.5 between what you get on a simple testing procedure and some important real world outcome, like how many times you get busted, is pretty impressive, really, but you still have a lot of room for error. Now, what you can do about this and what often is done about this goes beyond today's, topic, but often what you can manage is to improve your predictive power by using more than one measure. Ideally, you've got separate measures that aren't just kind of repetitions of the same thing. So if I'm using IQ, say, as a predictor, ho hum, but yeah, it's standard, thing. So I'm using IQ as a predictor. I wouldn't want to say, oh, I know, I'll use another IQ test as well, because they're kind of redundant. But if you wanted to find some other thing that was predictive of, okay, we'll make it college grades, that was not too strongly related to IQ, that could add to your predictive power. So then you start thinking, what else correlates, with grades in school? And, there's trait conscientiousness. High C people do more of their work on time and as assigned. And therefore they get higher grades. And you kind of add that. And what you often do is to combine these predictors in a statistical model. Most frequently you'll see some form of multiple regression technique. And basically what you're doing is saying, I've got 1, 2, 3, or however many predictors. I'm going to smoosh them together somehow and see how well cumulatively they correlate with the outcome. And again, this is beyond the scope of what we're talking about here, but the underlying idea in research or applied research is to generate a predictive equation that uses all the valid predictors you've got and kind of, again, amplify your ability to know or at least estimate what's going to happen. So yeah, here's an example, right? Oh yeah, use SAT scores, GPA, and conscientiousness, and however well each of those predicts, they kind of get thrown in with a certain amount of weight, which is literally a multiplier with them, and then maybe you can do a better job. Now, confidence intervals, yep, they're a thing. You might remember this with standard error of measurement. It's the same general idea. I'm generating a specific prediction, but there's room around that prediction. That's what the standard error of measurement is telling us. So what I can do is to say, I am this confident. Name your degree of confidence, can't be 100%. So I could say I am 95% confident that the true outcome will fall within this range. And that would mean roughly within 2 standard errors of the estimate in either direction. So if I'm trying to predict, how much you're going to earn in commissions as an insurance salesman in the next year, and my point prediction is that it will be $180,000, but there's a standard error of the estimate of $30,000 on that. I could say that I'm 95% sure that you will earn between, let's see, 180 minus 30 times 2, $120,000, and 180 plus 30 times 2, $240,000 in commissions. Those who've taken or are taking my assessment classes know that when I assign the work here, I always use either 68% or 95% confidence intervals, because the multipliers then you can round off to 1 and 2, and it's just easy. Now, what we're doing is recognizing that there's random error in our predictions, that there are variables that we can't control, that didn't measure, that are going to come into play. Okay, if you wanted to do this and make up the number you want, first off, you can go and look at my little presentation on the standard error of measurement. But what you're going to need is standard error of the estimate, the level of confidence you want, you can name it, and a table displaying the area under the normal curve found in the back of every basic statistics textbook, also easily found on the web, also found in this slideshow, but though it's going to go by pretty quickly. So you find the multiplier for your level of confidence, the one you picked, it's not my fault, it's your doing, in the table, multiply it by the standard error of measurement, and then you take your point prediction, and the confidence interval is that prediction minus the number you've come up with up to the point prediction plus the number you came up with. That's the table in question. Again, they're all over the place. So just as one example, if I wanted to set up 75% confidence intervals, well, I'm going to go in here and look at the Z to mean column until I find the number closest to 0.375. That's half of 0.75. So I kind of scroll down and it's like, right in here somewhere. So it's about halfway in between. Let's just say 1.15. You're going to be close enough. And that would be it. So, what I would say is, here we have Wackford Squeers eligible for parole next month. And we, use our predictive equation. And it says that he will most likely have 22 parole violations in the next 2 years. But that's, again, not really, I shouldn't say most likely to, that's the midpoint of our range of predicted outcomes, really. So the 75% confidence intervals, remember we had, a standard error of the estimate of 3.57, and we just looked up the 75% multiplier, it's 1.15. So we take that, those two numbers, we multiply them, and we get 4.1. Let's just say rounded to 4. I mean, you either violated parole or you didn't. You didn't have a tenth of a parole violation. And we'd say, all right, 22 minus 4 is about 18. 22 plus 4 is about 26. So we think he's probably going to have between 18 and 26 parole violations. So 3-to-1 odds, he's going to have more violations, substantially more violations, really, than the average person being released. And he's a bad risk for release at this time. We don't want him starting up any more Yorkshire schools. If you don't know that reference, look up Wackford Squeers and you'll find it. So, again, predicting individual cases, there's a lot of play around our predictions. Because the standard error of the estimate tends to be pretty big. And that's just how it is. Individual prediction is difficult. We look to improve it in 2 ways. First, instead of always predicting the average, we are generating individualized predictions. So we're improving on random guessing right away. You don't have to say of any man you're about to meet, he's probably 5'9" tall. If you have a formula that enables you to predict height from shoe size and the guy's shoe size, you can generate an individualized prediction. Some error around it, no doubt. I'm not even sure why you wanted to predict that, but if you did. The confidence intervals also are smaller than the standard deviation. Not always a lot smaller, but they are smaller. So we have an individualized prediction with relatively less play around it. Side note, then we'll be wrapping up. What about our colleagues over in the political science department? Well, as you may recall, pollsters are using different statistics than we are. But conceptually, what they're doing is very similar to what we're doing in psychological and educational testing. So again, you may recall that the margin of error of a poll is analogous to the standard error of measurement. So when they say the standard error, I'm sorry, the margin of error of poll is plus or minus 3 points, they're essentially giving you 95% confidence intervals around the polling outcome that they're predicting. So that's the confidence intervals for what would happen if the election were held today, check, and our sample closely resembled the electorate, that is, the people who actually show up at the polls and vote. So to the extent that we've matched the true electorate in our poll taken, perhaps a month before the election, we only have to worry about the margin of error. But the fact is, you don't know who's going to vote. So this is where there's a certain amount of craft, almost artistry to polling. They need to make an estimate. What will the turnout among, say, 20 to 25-year-old first-time voters be? What will the turnout among African American men in North Carolina be? They're needing to make educated guesses in these areas. They are not likely to be exactly right. And that means that the amount of error in predicting the actual election outcomes is going to be somewhat greater than the margin of error of the polls. That's like the standard error of the estimate. I have, by the way, read in something written by a professional pollster that in his guess, his educated guess, the actual error around the prediction is probably as much as 3 times as great as the margin of error in a given poll. I'm not sure where that number comes from, so don't quote me on it if you don't find it anywhere else, but it's kind of a useful frame of reference. All that said, we're wrapping up. The standard error of the estimate is the extent to which random error affects the outcomes we're predicting using our tests, our assessments of whatever nature. We can construct confidence intervals around those predicted outcomes and thereby delineate a range within which the true outcome is going to fall at whatever level of confidence we specify. Always remember, though, unless you have exceptionally strong predictors, there's going to be quite a bit of potential error when you're dealing with individual people, an individual student, an individual patient, an individual employee, etc. But sometimes, if we combine several of these relatively weak predictors, especially ones that are relatively independent of one another, into a single equation, say using multiple regression or some other technique, we can make rather more precise predictions. And actually, that is going to be that. So we're going to stop the recording and say good day.